Hi. Thank you all for coming to our presentation. This is what we spent the last year of class doing. We made a guided rail sanitizer for our EDD class, and we hope you enjoy the presentation, which will outline what we had.
All right, so I'm Jack Williams. I'm a senior, and I'll be attending UW Milwaukee.
I'm Luke Funk. I'm also a senior, and will be attending Michigan Tech.
I'm Mason Landish. I'm also a senior, and I will also be attending UW Milwaukee.
So for the first week or so, Raider gave us our outlines for constraints we had. First, it had to be a fully functioning product by the end of the year, and if it didn't work, we had to do a lot of extra stuff, which kind of gave us the boost in finishing it. The school gave us, every group, $200 to work with, and if we needed more, it just had to be basically our own money. It had to be an unsolved problem and a completely original idea. And our first 2 days of class was just filling out notebook sheets with just problems we encountered in life and which ones we could solve. And then most of us have been in these classes all 4 years, so we really wanted to show true engineering ability and being able to solve the problem completely.
So once we had our initial idea to base it off of, we had to come up with a problem statement that would outline the whole rest of the year, what we would be working towards for the entire year. And we, especially with the COVID-19 pandemic that hit our school year, we decided that the current method of sanitizing tables is ineffective and very inefficient. So we wanted to better that and fix it as best we could.
After coming up with our problem statement, we started brainstorming possible solutions. Some of our main solutions were a disinfecting Roomba, a disinfecting drone, disinfecting ceiling track, so essentially that, but it would be on the ceiling. And then we had our table track design. To basically choose between those four, we created something called a decision matrix, which essentially took the characteristics of what we wanted our solution to have, and it gave them point values. And this one ended up having the most points, so that is why we chose to design this one. This right here is called a Gantt chart. So a Gantt chart is essentially a chart that gives us our tasks, it lists them for us in a certain time period. So it allowed us to stay on track and keep us focused on what we needed to do. This right here is the fourth quarter. For the first quarter, we spent it coming up with this problem statement, coming up with possible solutions, and deciding. And then second quarter was used to research parts and come up with our final design. Third quarter was used to build our first prototype, and then fourth quarter was essentially for us to finalize our first prototype.
So like I said before, we had the $200 budget, and we didn't really start ordering parts until a little bit before Christmas break, and some of the parts had to come from China, which did take a while, and some parts weren't even really what we needed. And so out of the $200, we ended up spending a little under $170, and we still have $31 to spend on a party or something. We ordered from a bunch of different websites, including AliExpress, which is a Chinese company. Matter Hackers gave us the filament. Servo City was wheels, and Amazon and Tool Planet just gave us the motors and other parts.
And then the picture you see at the bottom right is our main list of parts that we had. So we needed ABS plastic to 3D print the various components, which we'll go over later. The wheels to have it, move across the track. The motor to propel it forward and backwards. The hose for the sanitizing solution to travel through the tubes and through the case. L-shaped connector, which we didn't end up using. We thought it would be more ergonomically better to have it more organized, but we didn't need it. The misting pump to pressurize the solution and push it through the tubes. Bearings and axle. We didn't end up using the bearings as we came up with a different design, and then the axle held if you can see the red wheels on there, just to keep it more sturdy. And then the tank to hold, which is now on the floor. But besides this picture, we actually had about 5-6 pages of just various options for each different part, because like Jack said, some of them would come from China, and we didn't have that kind of time. So we had very different parts, and we highlighted our best options that we had.
So this is comparing the 2 different tracks we designed. So the one on the left is the very first track we designed. Well, second track, because the first one actually had like little walls where the wheels go to keep them in, but we found that just kind of created more resistance and friction, which just slows it down. Those circular pegs actually really caused some trouble because every time we'd print new ones and how to go to attach them, they just break. And so in the end, we had like one piece of track that had all 3 pegs attached. And then so a few months ago, we designed the one on the right, which we went to a more structurally stable with the rectangular prisms that worked a little bit more like Legos, and so they just kind of locked in and we didn't have to worry about them coming out. And then right there, it's a chamfer on the corner, so that made it so if the arm did make any contact, it wasn't a corner that was sharp and could cause a lot of resistance, so it just made it more smooth if we needed to be. And then here's the end pieces. It's the same concept, but we didn't even think about these until we designed the new track. It's the same kind of deal, just on the end.
And the end pieces, actually, for the track itself, we had more of a tighter fit so that they'd be sturdy and stay together, but for the end caps, we made the sizing like bigger or smaller depending if it was the peg or the hole, so it would easily slide back and forth when we were testing it.
So this right here is our arm piece, which is the main piece of the device. The picture on the left is our first design, and the one on the right is our new one. It might be difficult to see because it's rotated, but our new one is taller to help spray the mist a little farther. Also, the motor case is a full cylinder, which holds the motor more stable than having half of it and then having a second piece on top. And then also we added a little case for the misting pump, which we actually ended up having to adjust to make it fit. And then the last major change was the little pool right under the nozzle, which essentially collects droplets from the nozzle and then it runs through the hole back to the other side, which would then run through a tube back into the disinfecting storage.
So building probably took the most amount of our time this year because it was a lot of trial and error. This picture right here is when we first got that misting pump that actually disperses the sanitizing solution. And so we hooked it up to the power supply and a little cup of water and just saw how it worked and how it behaved. It was a lot of very rudimentary techniques we used to attach things, such as zip ties. We use a lot of those, which doesn't look very, very nice. And then this right here is the final product that just broke. We used to have batteries right there, battery holders for lithium-ion batteries, a voltage regulator, and a button all attached that me and Luke took a lot of time to solder, but it ended up just giving problems with us. Lots of errors with things not moving or wires coming loose, so we decided to just take them all off and just have it run off the power supply, which made it a lot lighter as well, but not light enough where the tank and the motor still weighed it back a little bit. So we took a little trip to the metal shop and got some scrap metal and stuck it together and put it on the arm, and that actually worked really well. And we went from using zip ties, as you see here, to just some hot glue, and it worked pretty well. That's also the second Arduino, what Mason will touch on later. It basically runs the whole arm. It's the second one we used because the first one we kind of cooked. Yeah.
So this is the Arduino. The Arduino, as Jack said, controls the arm, so it's like a mini computer in a sense, but we like to think of it as the brain. It tells our misting pump and our motor what to do, when to do it, and with what speed and such, because we need specific timing for our project specifically. So for our project, compared to others, there wasn't as much coding, but we still had some coding. There was about 31 lines, I believe. We used it for writing the code and connecting the components to the machine. So there's lots of wires connecting from the motor driver, which we will touch on, the Arduino, and then the actual components being the misting pump and the DC motor. And since we only had 31 lines, it didn't take too long, but it was still a struggle since none of us had any past experience with it. So all those days that we were cooped up in our rooms doing virtual learning, we were just watching YouTube videos on how to do it because we had no idea. So that guy at the top right had a full like 70-part series and really taught us a lot. So
Shout out Paul McCorder.
So this part right here is the L298N motor driver as seen in the other presentation. This motor driver essentially allows us to control the speed and direction of both of the motors on there. As you can see, the 2 blue pins on the left side were used for the DC motor, which is the one with the wheels on it. And then the 2 pins on the right side were used for the misting pump. The 3 on the bottom are power and ground. We ran the 5 volts into the Arduino to power that, and then the 12 volts in ground. The ground is also connected to the Arduino, and the 12 volts was for the power supply. And then next to the power and ground, there are 6 more pins. The 2 outermost pins are used for the speed, as you can see the 2 blue wires on the picture below. And then the 4 pins in between those are used to control the direction, which are the yellow wires in the picture below.
So this was our coding. Like I said, there wasn't a whole lot. We only have 31 lines. On the left side, the bigger picture is our setup. So in order to do what was on the right side, we had to tell the Arduino what was plugged in where and basically what it was. So none of these were inputs like a button would be. So we were just output, like telling it what to do. And then the setup would be plugged in to various pins that were labeled on the Arduino.
The picture on the right is the code that you actually see working. It is the loop part of the code. This was changed many times throughout the semester, but in the end we ended up using what is called a PWM signal, which essentially means that the motor will run at its max speed for a small amount of time, and then it will turn off for a small amount of time. So in our case, it was on for 20 milliseconds and then off for 30 milliseconds. And in this code, that loops 80 times, so it will repeat that process 80 times, and then after that, it will then stop for 2 seconds when it reaches the end of the track, and then it will then repeat that process again, except moving in the other direction, and it will loop 80 times. We needed this because our motor has a lot of speed, but not a lot of torque. So to overcome any friction against the side of the track, we had to use the PWM signal.
So as I said before, as soon as we got the pump motor, we had to test if it actually worked. And so one end you plug into where you're getting the liquid from, the other end you plug into, in this case, the nozzle. And so we just got a piece of cardboard after we got it and just wanted to see how far it actually went and how wide the spread was to see if it actually did what we wanted to do and make sanitizing big tables easier. And so we just let it go, and it got about 23 inches away, and the spread was about 4.5, 5 inches, which we thought was pretty good because it's pretty concentrated right there. So if you're sanitizing a bar or a lab station here or something, it covers everything you really need it to. So we also had to test a lot with the motor. It was a lot of trial and error with all of us because we had a lot of issues with the wheels rubbing on the track and the motor making the little sound it says to let us know it's not working right. A lot of the thing almost falling out of the track because it goes too fast. A lot of it barely moving. I remember when we first got it, we just put it on max and saw how fast it could go. We played with that for like 20 minutes. But we were pretty happy with how it turned out until right now because it kind of broke. But yeah, it was a lot of setting it up, letting it run, seeing how it behaves, seeing how long we need to let it run, how fast it needs to go, how long it needs to stop, making sure everything is working as it should.
So right there is a picture of our final product. Yeah. Some new things that we added to the final one were the counterweight, because without it, the arm would lean to the side, which would not allow the motor to actually move through the track. So the counterweight balances it and keeps all 4 wheels flat on the track. And then also we added the holder for the misting pump, and then
Like I said before, we did take a lot of stuff off. Like right there used to be holders for lithium-ion batteries, but between one just exploding and them just being tough to wire, we kind of just took those off. There was a voltage regulator right here on a little board that made sure that no more than the 5 volts we needed was going to the motor driver, or else it would just fry it, and that was already our second one. We had a button up top that just gave us issues as well, so we decided to take it all off and make it a little more simple.
And then this is our final video of it working. So basically, it would start, come forward, and then it would go backward. And if you notice, sometimes, what we want it to do is when it comes to a stop, we want the top motor to also come to a stop, because in an actual business point of view, we'd have it go and you wouldn't have it be running continuously. We just had the speed what it is just to demonstrate it. In an actual scenario, we'd have it run and then it could sit for an hour or an hour and a half or however long that business wanted it to sit, and then it would go again. So that's why it shuts off. And we were, if the audio was in, we all scream when it comes back finally, because this was like 30 videos in, just deleting, and we finally got it.
Many hours after school as well.
Yeah.
And so we just want to give a quick thank you to the class and Mr. Rader for making what would have been a sucky year just something pretty fun. And for Rader for dealing with all of our selves. It was actually a really fun class. While we did do work, we also just had fun as well. All just messing with each other and celebrating whenever one project worked. Everyone was turning on breakfast machine because we didn't think it existed for a while. Yeah, it was just we had a blast overall, and it was a very fun process, and it's very rewarding in the end.
And also, the project that we had today wouldn't be the project without our class. For each project, everyone was going back and forth, giving helpful suggestions, and like Jack said, applauding when one thing would happen. So just thank you.
And if anyone has any questions, now's the time.
So, in the video of it working, why does it look like it just fell off the track at the end?
Movie, sometimes things don't appear as they are. And this was when we were still testing the speed, so we wanted it came to more of an abrupt, oh, there it goes.
I promise it doesn't fall.
It's to add suspense, to keep you on the edge of your seat, looking forward to our performance. But once we put the end caps on and we were testing it out there, it would kind of just hit the end cap and wouldn't fall off as much.
We also had other angles, but it was very tough to send it in between and putting it in the PowerPoint and everything.
Okay, and I saw, what was the inspiration for the letters DAD on your project?
It was actually your Adidas soccer pants. The letters were coming off, and you gave us 2 D's and an A, so I just had to. And we made it into an acronym. Disinfecting autonomous device.
Did you do any research or any other thoughts on different nozzles and try to get trajectory or try to get it out further, more of a mist instead of a beam?
Yeah, I actually, in the beginning of the year when we were researching parts, I did look into the different sizes and types of nozzles. And with the pump that we have, it only creates enough pressure for this nozzle, well, other nozzles too, but this one created more mist. But also, this misting pump is a 24 volt motor, and our motor driver only allows 12 volts, so it's not working at its full power, but it creates enough pressure for this misting nozzle.
And sometimes the nozzle, it does do like a jet stream like that for mysterious reasons. Sometimes it does do the mist, like when we were testing it, so we don't really know.
Yeah, it's going to be for you now. So I got a question for you more on your process than on the project, as I saw the project run. So you guys went through, you first generated concepts, right? You did a decision matrix, then you did a timeline, and then you looked at parts, and how long does it take to get there, and then you worked out the whole plan of how you're gonna put it together. That's all great stuff. That's all perfect for engineering design projects. Was that part of this class, or is this over the 4 years?
That was all part of this class.
Nice.
All right, nice job. Thanks, guys.